Hello everyone and welcome to my YouTube channel. In this video we will see how we can use these AI platforms for programming, and in this video we will try to code for the vapor compression cycle, which is the main cycle used for the heat pumps or refrigeration. So let's start. So this is the ChatGPT environment, and we will just write provide a vapor compression cycle code and import thermodynamic properties from CoolProp. Here you can see that within second it will provide us a basic Python vapor compression cycle code, and it is importing the properties from CoolProp. So I would also explain why we are using this Python environment, and why it is better, because in this video we will try to use all the freewares. So Python is a freeware, and the environment we are using is PyCharm. It is also a freeware, and the CoolProp, which is a library inside the Python, is also free. So our aim is to utilize all these freewares and see how deep uh, research work or programming you can do with these resources available. So here you can see it has provided us the four state points, and it has also assumed isentropic efficiency, condenser outlet, throttling outlet, and evaporator outlet. Let's just copy this and paste it into our Python environment. And name it VCC and chat GPT-1. Now we will run this. So here it has also provided us with the TS diagram, which we can see is not correct, because you can see, like, after the compressor outlet it's not cutting the dome on the vapor cycle or the vapor line, but it's going straight to the condenser outlet. So, and here you can see it has provided us the evaporator pressure, condenser pressure, compressor work, refrigeration effect, and coefficient of performance. So here you can see, like, just writing to ChatGPT what we need, we can just get this code. So those who don't need how to do coding and they want to do some research work or study, or like refrigerants comparison, so it's now very easy to just use this chat GPT or any other platform, Grok, and you can just get these codes. And other most famous platform is Grok. So let's see how Grok respond us when we ask Grok to provide us the same basic code. So here we have pasted the same question, and we have asked to provide a vapor compression cycle code and import thermodynamic properties from CodeProp. So let's see what the group provide us. So here it has also provided us with a Python code, and it is also importing properties from CodeProp, and it is also taken refrigerant R134A and evaporator temperature of 0 degrees Celsius and condenser at 40 degrees Celsius, and 10 kilowatt duty with an isentropic efficiency of 0.8, and it has also given us the state points after the evaporator, compressor, condenser, And here we can see mass flow rate calculation, compressor work calculation, condenser heat reduction, and coefficient of performance. So we'll just copy this code, and what you have to do is to make a new file in PyCharm using the Python environment. And let's name it VCC and Grok 1. And let's paste the code here. Now we will run this code and see. So here you can see the results. It is giving us the evaporator temperature, condenser temperature, the mass flow rate in kg per second, compressor work, cooling capacity, condenser heat rejection, COP. So here you can see like Grok has provided us more details, which are the most important details for a basic vapor compression cycle, like mass flow rate, compressor work, cooling capacity, and condenser heat duty with coefficient of performance. And it has also provided us all the state points. It has not provided us the TS diagram, but we also did not ask for that TS diagram. So here you can see like Grok and ChatGPT response on basic vapor compression cycle. Now, what we want to go a little bit deeper, and we want to know like which refrigerant is better, or we want to compare different refrigerants. Like in this nowadays, we want some low GWP refrigerants, and we want to make a small program in which we can see which refrigerant has a better performance as well as a low GWP. So as we have seen, like Grok is providing us a better result. So let's ask Grok. Here again, we will ask him uh, provide code in which we can compare different refrigerants, right? And we can say it detailed code, right? Or detailed VCC code. And the second thing is like to assess these refrigerants, it is desirable to see their pH diagram or TS diagram. So for instance, let's ask also provide the pH diagrams along with refrigerant domes, so we can access which refrigerant is performing well. So we will get these detail about all these refrigerants. So let's see how Grok responds now. So here it has provided us, and it is saying like simulates vapor compression cycle, compares COP, and provides pH diagram including the saturation curves of VCC. So this is the code. You can see in seconds it has provided us the code where we can change the evaporator and condenser temperature or the duty, and we can change the isentropic efficiency. And here you can see like it has provided us with four you can say most famous refrigerants: R134A, R410A, R32, and ammonia, which are mostly used in this vapor compression cycle due to their better thermodynamic properties. And here you can see this is the code, four state points, and it stores the results and then it plots. So it generate pH diagram, and then it also plots all these state points inside this pH diagram. So let's copy it, and now we will make another file, and we will name it Grok pH comparison, and now we will paste it. Now we will run it. So here you can see this is the performance matrix for R134A with the COP 4.40 and mass flow rates and compressor work and all the state points. Similarly, this is for refrigerant R410, COP 4.09, and here is R32 with the COP 4.27, and here with the refrigerant ammonia with COP 4.63. So 4.63 is the highest, and 4.09 for R410A is the least. So this is the general comparison between these refrigerants, and it is saying us like it has saved the pH diagram for the refrigerants. What we want is not to save diagram but to give us a view or a show diagram. So we will ask him not to save diagram but to show diagram. Show or display it. So here we have asked him not to save diagram but to show or display it. So it says like it has amended the program accordingly, and instead of saving the diagram, it will now display the diagram when we will run the code. So here it is revising the code, and here it is, you can see plotting for pH diagrams, printing the results, and here now we will copy this code and we will again paste it. Now we will run it. So here you can see now it is also showing us the pH diagram where pressure is on the y-axis and enthalpy is on the x-axis, and these are the four state points, and here you can see is the liquid saturation line and the vapor saturation line. So this is pH diagram for R134A. When we will close it, it will show the pH diagram for the next refrigerant, which is R410A. And here you can see the pressures and the enthalpy values. When we will close it, it will display us the pH diagram for the next refrigerant, which is R32. So here you can see pressures and enthalpy values. But our concern was not to show these pH diagrams separately. In this way, we cannot compare the pH diagrams of these refrigerants. So our main aim was to display all these cycle diagrams together in one plot so that we can compare these refrigerants, and we can see which one is performing better, which one is giving the least pressure drop, and which is giving us the more enthalpy, and which is giving least uh, how the compression ratio is working and other like important points. So now what we will say, we will go back to the grok and we will ask for, please provide single pH diagram for all the refrigerants, domes, and cycles in it, so that we can compare these refrigerants, right? So now you can see, to compare VCC on a single pressure enthalpy diagram, it will modify the code to plot the saturation domes of all these refrigerants on one figure using different colors of each refrigerant, and the code will use similarly Colprop for thermodynamic properties and Matplotlib for visualization. And the pH diagram will display the saturation domes and VCC cycle state points for each refrigerant with a legend to distinguish them, and the diagrams will be displayed using plot show. So here you can see it has provided us the code, the new code. Now we will just copy it and we will go back to our PyCharm environment, and here we will create a new file and we can say it grok pH comparison 1, and we will paste it here, and now we will run it. So here you can see the diagram. Now you can compare these refrigerants. Here you can see for R134A the liquid line is blue and the vapor dome line is dashed, and the state points are solid lines with points. And here the red is for R32, the green is for R410, and the purple is for ammonia. So the purpose of seeing all these diagrams together is now you can see the difference between these cycles. The ammonia is a quite wider dome and providing a lot of enthalpy during evaporation as well as during condensation. And in this pH diagram we can also see the pressure values where your operation is occurring. So it is in bars. So this is 10 bar, 9 bar, 8, 7, 6, 5, 4, 1. So usually it should be above 1 bar. If this is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So this is 1, this is 2, this is 3 bar. So you can see that R134A, it is above atmospheric pressure. So and you can see the pressure drop which is occurring in R134A, and you can also see the pressure drop which is occurring in ammonia, and you can also compare these pressure drops with R410A and R32. Here one of the important thing for the pressure is you can see that R410A and R32, they are working on higher pressures. For example, this is 10, this is this is 20, this is 30, 40, 50, 60, 70, 80, 90, and 100. So here you can see the outside pressure is between 20 and 30, around 25 bars, whereas for R134A it's around 10 bar. So you can see it is twice the value of R134A. So the system is working at higher pressure values. Even the evaporator is operating at higher pressure as compared to R134A and ammonia. So here you can see, like, in a one figure you can just compare different refrigerants and you can see which one is your desirable refrigerant. Like if you want a low pressure operating system, high pressure operating system, or natural fluid, and you need high enthalpy values and less mass flow rate, reasonably, because it has like a high kilojoule per kg enthalpy value. For ammonia it will have less flow rates, and if it has less enthalpy change values, it will use higher mass flow rates, and mass flow rates also you can see affects the COP of the systems. So all these small things you can see in pH diagram. So if we will see, I think this ammonia is best performing here because its pressure values are also not as much high as these are 32 and R410A, and its enthalpy value is quite high, so it will has very less mass flow rate. But usually the issue with ammonia is that it is flammable, and it is also toxic, so it comes under the ASHRAE safety conditions of B2. So that is actually the main reason why we don't use ammonia. So this was the main reason of this video, so that you can just compare different refrigerants. And what we can do further, for example, if you want to compare some other refrigerants, you will just change the name of the refrigerants here. For example, instead of ammonia, we want to see how propane behaves, and instead of R410 we need butane, and now we will just run it. So here you can see now the plot is completely changed. The ammonia is removed, and instead of ammonia you can see this butane, and you can see this propane, and you can compare all these pH diagrams. In one glance you can just see which is best. So here I would say, like, butane, which is nowadays mostly used in most of our refrigerators, is is performing good. You can see it is providing us a large enthalpy change values with the normal pressure drop, and also you can say it is just above the atmospheric pressure, and evaporator is just operating at one above 1 bar, which is the most desirable. It's not operating at very high pressures and below the atmospheric pressure. And the outlet is, you can see, is 2 3 4, less than 4 bar. So it is providing us the largest enthalpy, it will have the least mass flow rate, and it is not giving us much pressure drop, and it is operating at lower pressure as compared to others. So here you can just see, like, butane is best among these. Also butane is natural, but again butane is highly flammable and it comes in A3 category. So also propane is highly flammable and it comes in A3 ASHRAE category. And in case of flammability, where we cannot use flammable refrigerants, we cannot use these two refrigerants. So here you can see like how we can just with a glance or without any language programming language skills, you can just use the AI platforms like Grok or ChatGPT, and you can write code and you can use it in your research. So here you can see it has also provided us with these results, the COP values and the state points, and it has also provided us with the graphs. So here you can see in this our 134A has a COP 4.4, butane has 4.59, and R32 has 4.27, and propane has 4.32. So if you just want to compare the COP values, you can see, as I told you, butane has the best pH diagram plot, so its COP is better. Now you can also compare the mass flow rates. Our 134A has a 0.07 kg per second, and here you can see half than that R134A, it is 0.03 kg per second. And not only its mass flow rate will be less, but also the charge of these natural refrigerant is less as compared to these HFCs. So for R32 it's 0.04, and for propane is 0.037. So butane is the best among these four refrigerants. Here we have seen how to plot graph and how to compare different refrigerants and how to plot their pH diagram. So in next videos we will go into much more details, and we will see how we can use these AI platforms to get more detailed vapor compression cycle points, which will also include superheating, subcooling, and isentropic efficiencies, so that we can get some realistic results. So thank you very much for watching this video.